This is a great time to get together. This is our actually 7th Colloquium breakfast. So we've been enjoying these for last year and into this year. We have 6 departments in our college, so we've gone through all 6 departments and are on our 2nd cycle back to math again. So it's kind of fun and exciting to do this. I've looked forward to these each time. It's really fun to hear faculty talking about the things they do and their excitement about doing their research, and most of them what they're doing with their students, and they're highlighting the student work, and that's just really fun to see. We started this fellows program of a way to get friends and alumni together because we wanted to get people to know more about our college and what we're doing here at Cal State Long Beach. We have great alumni in the community, and we have a lot of friends we've made, collaborators. And so this is an opportunity to bring people together, to get to know each other better, to learn more about what we're doing. And so that's why we highlight a department each time and highlight the research of a faculty member and what's going on in that department, just so you get a better sense of some of the things that we're doing. And we're really pleased today to highlight Dr. Jim Stein from the Department of Mathematics and Statistics, and we'll hear more about him later from his department chair, and let Robert introduce him. Here at Cal State Long Beach, we're all about students. That's what we're here for, is to educate our students. And the mission in our college is to really do our best to prepare and train our students in a way so that they're very highly prepared to go out into graduate programs, professional programs, and out into the workforce. Our students go into government, academia, education, K-12. They go into industry in all areas. And so we feel it's really important that we train our students well so that they are highly prepared to go out and take their place in the community. And because we're highlighting the Department of Mathematics and Statistics today, I would just like to emphasize what this department does in the way of preparing our students. Every student who comes into this university has to take at least 1 math class. And this ranges anywhere from pre-baccalaureate classes, because we do have students who come who are not ready to actually start a college level courses yet, all the way to master's level mathematics courses. And that's an awesome responsibility for a department to be. Think about it, you have to be responsible for the math of every student in this university, and we have like 38,000 students, so that's kind of a big job. And I just want to commend Dr. Robert Mena as the chair of the department. He just does a superb job of making sure we have what we need for the students in the university. And in addition to, preparing math majors and math teachers, that department supplies all of the math courses for all the science and engineering students. So that's a big responsibility too, in preparing our students to go out into STEM careers in the workforce. We have a national problem of not having enough people in STEM workforce, and so it's one of our part of our mission is to make sure we're preparing more and more students for that and that they're better prepared, and the math department certainly helps tremendously there. I think we have a number of measures that we are doing well in what we do here in the college. Our students really do go off to top-notch graduate programs, the Stanfords and the Harvards and all the top-notch schools. Our students get there. PhD programs, MD programs. They get into professional programs at really top-notch schools. And our students are in demand in the workforce out there. We have people who call and say they want our students. When we talk to people in the industry, they really do like how we prepare our students. And that's really great to hear. We also hear from our alumni who come back and tell us what a great experience they had here. And oftentimes it's that one class or that one faculty member or that research experience that was career or life-changing for them in many cases. There are people who are struggling, and that one faculty member just made a real difference for them. And we're really proud of our faculty. And that's what it's about, their job here. They love students, they care about students. They make a difference in the lives of our students. And it's always great to hear our alumni. Mary Ann hears this often when she's out talking to our alumni. And it's really great to hear how much they appreciate our faculty and their experiences here at Cal State Long Beach. We also have a lot of collaborations in the community that we're really proud of and to be a part of, and these include other colleges within Cal State Long Beach. This also includes our community colleges, Cerritos and Long Beach City, and we have a number of colleagues from Cerritos today. You want to wave your hands over there? Anybody from Cerritos? We appreciate the collaborations they do with us, particularly in the math and science teacher preparation. It's just a wonderful working relationship we have with them. But we have a lot of other wonderful collaborations. I mean, we're working with some developers at PCH in Second, where we may have a science learning center down there. We're working with the Port of LA on moving one of our marine facilities over there to have a new and expanded marine thing. So we do a lot of things with our community as well as our alumni, and we're really pleased and proud to have those kinds of relationships. It's important that we maintain those collaborations. You know, that's how we can best serve our students, that they have these kinds of opportunities. So again, this is why it's so important to have you here today, to learn more about us, to build those collaborations within our community. So thank you for coming. We really appreciate the part that you play in the lives of our students. I'd like to now give you a few updates about what's going on in our college. I had announced last fall that we had 5 searches going for tenure-track faculty members. And these are in inorganic chemistry, math education, theoretical physics, experimental physics, and systems physiology. And at the time I said with the budget, we're hoping that we can go forward with all of these searches. Well, in January, our chancellor announced that we had a freeze of all hiring within the CSU system, and that only hiring would go forward for those cases that were exceptions for critical needs. Well, fortunately, the day before, we had sent out a hop to one person for the inorganic chemistry position, and so I'm pleased to announce that we have Dr. Shahan Tharakshan, who will be our inorganic chemist coming in the fall, so we're pleased to have that position actually filled. But we have a provost here who also really has a vision and moving forward, and I'm really pleased that she felt that we still needed to go forward and hire a tenure-track faculty. So she did approve our other 4 searches as exceptions. She saw the need we have here, and she based that need on things like we had bottleneck courses where we really needed to hire more faculty to help students get through. We had critical courses where they couldn't be taught because we didn't have faculty and our students need them. She was looking also to make sure that we had high-quality candidates. And in our searches and our pools, we had that, and we had those needs. So she did approve the exceptions for those 4 other searches. So we've completed the interviews for the theoretical and experimental physics, and I anticipate making some offers probably by the end of next week. We also have the math education moving well along, 3 candidates in and 1 more next week. I anticipate we'll make an offer there. Really great candidates in all these searches. The systems physiology one is not as far along, but actually we'll be doing telephone reviews hopefully soon. So, but we hope to hire in all of these positions, and it's going to make a real difference in bringing in new faculty, the excitement they bring, the research they bring, the working with our students, you know, and filling critical needs that we do have within our college. For any of you who've walked past the construction site for our new Hall of Science, or been reading the paper lately, you'll know that that building construction was put on hold. We have a big hole out there. With the rain, it's turned into a mega-sized Olympic swimming pool. But it will dry out, and the budget will get better, and we will commence building of our science building. We're not sure when we'll be able to get it started again, but we're very optimistic that it will happen hopefully soon. And I just want to remind you that we do have some great naming opportunities in that building that will make a real difference for our students. So if any of you have an interest in a naming opportunity or an interest in helping our students, please see Marianne Horton. And Marianne, you want to raise your hand? Marianne loves to talk to people who love to help our students. And despite the budget cuts, you know, great things are happening. And, you know, I have such an optimistic and wonderful feeling about what's going on now. And I go, why is that? Because the budget is so bad. But, you know, I think it's because everybody's just coming together. You know, they realize that, you know, that we have to do with less in some areas, but they're just still excited about working with students and doing things. And I don't have time to talk about all the things, but I do want to share some really exciting news we just got recently. Dr. Jean-Louis Bou in the Department of Chemistry and Biochemistry and Dr. Thomas Gredig in the Department of Astronomy, Physics and Astronomy just received news in the last couple of weeks that they're getting NSF Career Awards. Now, for those of you who don't know about NSF NSF Career Awards. This is really exciting. These are highly competitive, very prestigious awards for faculty who are early in their careers. Dr. Boo is in her 6th year here, and Dr. Gredick is in his 2nd year here. So to get these kind of awards at this point in a career is just fantastic. And they have, these are 5-year awards. Dr. Boo's is for about $600,000, and Dr. Gredick's is about $450,000. So these are major awards. And their budgets include support for undergraduate and graduate students to work with them in their research. So that's the exciting part too. Dr. Gredick was telling me that when he looked at the NSF website, about 35 awards were made nationally. And we have not just one, but we have 2 of those here at Cal State Long Beach. I think that tells you the quality of our faculty we have here. You know, this is just really exciting. I mean, we're really proud of those 2 as well as all of our faculty. If you happen to see them, tell them congratulations.
In a recent article in the Wall Street Journal, they ranked 200 professions based on 5 ingredients: environment, income, employment outlook, physical demand, and stress. Lumberjacks came in 200. Dairy worker, 199. Taxi driver, 198. On the other end, in 3rd place were statisticians. 2nd, actuaries. And number 1 was mathematicians. Do nerds rule? Does math rock? Some among you have heard me talk about the kingdom of the nerds. The Department of Mathematics and Statistics is a very large department, as Laura has just said. Last fall, the department had 39 tenure track faculty, 42 lecturers, 22 teaching assistants, and 14 graduate assistants. It taught over 41% of the units of the college, for a total of 1,842 full-time students. That's a small university. Among almost 6% of the units of the whole university. 8,625 students took classes from us, of which 430 are undergraduate majors, and more than 165 are graduate students in 4 programs: Applied Mathematics, Applied Statistics, Mathematics Education, and Pure Mathematics. Our majors, both graduate and undergraduate, go on to a variety of professions. Some work in business and industry, such as insurance companies or manufacturing or healthcare companies doing analysis or actuarial work. Some go on to government working, doing number crunching. Many become teachers at the high school level in Long Beach and LA and Orange counties. Fewer, but still a significant number, as several of here are here, become community college teachers throughout the city, the state, and the country. And a select few go to earn their PhDs and take over my job. Recently I was asked, what does beach pride mean to you? My answer was as follows. There are at least 3 facets to that pride. I'm proud of our department because I believe we serve our students well. Indeed, I feel that our majors, both undergraduate and graduate, are better served here than at many other institutions I've had contact with. Second, I'm proud of our students who, despite facing many obstacles, go on and contribute to society in many ways. From Rafael, who's a successful teacher in a tough high school in LA, to Johnny, who's a professor of applied mathematics at Brown University. Finally, my pride consists of I'm surrounded by fabulous colleagues. One of them spends many weekends every year with high school students solving hard problems. Many of those high school students later choose mathematics as their career, but in any case, they treasure the experience they had as young men and women. The same colleague directs Math Day at the Beach, which is a great event coming up on Pi Day, every spring, to which many other faculty and students contribute. Another colleague is a nationally recognized author of mathematics textbooks, who is also an incredible teacher. And another who, besides being a masterful juggler, is also a great teacher. And the list goes on. And indeed, you're in for a treat from one of those fabulous colleagues. Jim Stein has been with us forever. A very well-liked teacher, great mentor and advisor, respected colleague, well-known researcher, brilliant conversationalist and lecturer. He's a nerd that makes us nerds proud. Alas, his lovely wife has told him to simplify his life since he's currently writing 2 other books, so he will semi-retire next year. And we're very sad that he's partially leaving us. But Jim will always be welcome in the department, And so I ask you to do the same and welcome Jim Stein.
First of all, I'd like to thank Robert for that nice introduction. And second of all, I'd like to thank whoever it was that had the idea to invite me to do this, because I just love talking to large gatherings. And finally, I'd like to thank you all for coming and supporting the university as you have both now and in the past. Millennia only come around once 1,000 years. And so my idea was that what they should have had was a man of the millennium. And I know who I would have nominated as man of the millennium. I would have nominated Isaac Newton, because Isaac Newton made the world basically the way it was today, the way it is today. Not only was Newton a fabulous mathematician and physicist, Newton essentially changed the way that we look at the world. Prior to Newton, the universe was a universe of mystery. After that, it was a universe of problems that could be solved. And Newton ushered in a spirit of what might be called intellectual optimism. And it reached its culmination with the following quote from Pierre-Simon de Laplace. I used to be able to memorize these things when I was younger, but remember, I came here just before Nixon left office, so my memory is fading. And also because Laplace was French, they're given to run-on sentences, so you'll excuse me if I breathe occasionally in this. Given for one instance an intelligence which could comprehend all the forces by which nature is animated and the respective positions of the beings which compose it, if moreover the intelligence were vast enough to submit these data to analysis, it would embrace in the same formula both the movements of the largest bodies in the universe and those of the lightest atom. To it nothing would be uncertain, and the future as the past would be as the present to its eyes. A beautiful statement. But one of the things that you can be pretty sure about Laplace is he never had to do what I have to do Friday. I have to take my car into the garage to get the brakes checked. And one of the things that when you take a car into a garage is they have a very annoying habit of when you call up and say, can I pick up the car? They say, sorry, it isn't ready yet. And there's actually a very good reason that they have so much difficulty. It's because they are facing a really difficult problem. Namely, the problem of scheduling repairs for the cars that come into the garage. And to give you an example of why scheduling is a more complex problem than other problems you might encounter, let me take a couple of others that happen to us in ordinary everyday life. First of all, let's suppose that you have to write the checks for the month. I don't know about you, but when the first comes around, I just write out all my monthly checks. Okay, you have a stack of bills, you have your checkbook, you write out a check, you put it in the envelope, you seal it, do another one, and you can see the stack of bills go down and the envelopes increase, and you can get a pretty good idea of when this task is going to be finished. And it takes you about as long to write the rent check as it does to write the check for the cable company, even though the rent check is a larger number. It's about the same amount of time. Now, another but more complicated task is if you happen to have a Rolodex and drop it on the floor and have to put all the cards back in order, in alphabetical order. You start this task by, we've all put things in alphabetical order, and it's very easy to do the first few cards in the deck. But as you get more and more cards, it becomes harder and harder to find the appropriate place for the card, simply because the deck of already sorted cards has gotten much larger. So this is a more complex task in that even though you can see the finish line, every card you add to the deck gets you closer and closer to the finish line. What happens with this problem is that the cards get harder and harder to sort at the end. Unlike it takes just as long to write the last check as it did the first, but the last card takes much longer to sort, unless it either ends with Z or begins with A, in which case you can slam it on the back of the deck or the front of the deck. Now, let's look at the problem that the garage faces. The garage has to do a very complicated scheduling problem because tasks at the garage sometimes have to be performed in sequential order. I wish my colleague Salim Watson had been there for me to talk to because he's an expert in auto repair. But my impression is that if you're going to replace the shocks, for instance, or check the brakes, what you have to do is you have to put the car up on the hydraulic lift. and before you check the, before you replace the shocks or check the brake. And also, what might happen is you might have mechanics of varying degrees of skill. Some can change the oil, but if they have to do complicated jobs like replace the timing belt, things like this, only certain mechanics can do certain jobs. And so what might happen at the garage is you're making out a schedule and it looks like you're through, and all of a sudden you realize that all 4 cars in the garage need the hydraulic lift at exactly the same time. So what are you going to do? Either you backtrack on reconstructing the schedule somewhat and try again, or you realize it's just too much of a mess and you start over. So this is a really, really difficult problem. And it's substantially more difficult than the other problems that, that we previously encountered. But what characterizes the 20th century is, for the 20th century, mathematics was brought into the picture in order to show that there were certain problems that were not only difficult, they were outrightly impossible. And they come from 3 different areas. One comes from our understanding of the physical universe. One comes from mathematics. And one comes from the social universe. And so let's put this on here and let's see if everybody can see this. Okay, I've stated the ideas fairly quickly, but in physics, most people have heard, especially at a gathering like this, have heard of Heisenberg's uncertainty principle, which says that it's impossible to simultaneously determine both position and velocity. Now, there's an awful lot of quantum mechanics going on here, and a lot of physicists have done a much better job of explaining this than I possibly could, so the lecture isn't going to involve this.
Velocity is not good. Momentum instead.
Well, I could have used, it's true, I could have used momentum. I could have put momentum there, but I wasn't sure everybody knew what momentum was, and they're pretty clear on velocity. Okay, so with mathematics, you have Gödel's incompleteness theorem. And this was an astounding result proved by the Austrian logician Kurt Gödel, in which he showed that there were true mathematical propositions which logic cannot establish. That's, when you stop to think about it, that's an amazing result from a philosophical as well as a mathematical standpoint. Because prior to that, mathematicians had thought, okay, if you take a mathematical proposition, either there's a counterexample to it or there's a proof for it. And Gödel showed that this was not the case. And finally, in the social universe, there's Arrow's impossibility theorem, in which he showed that there were limitations to translating the preferences of the individuals in a group to the preferences of the group. That's what we do when we vote. And that's what I'm going to discuss today. And in order to start the discussion, we go back a little before the French Revolution to someone named the Marquis de Condorcet. And Condorcet originally started out as a mathematician. In fact, his doctoral thesis was so good that one of the preeminent mathematicians at the time said, hey, this guy really has promise and should go much further. But Condorcet got interested in economics and politics, and unfortunately, come the French Revolution, he made a wrong choice of who to ally himself with. Ended up in the Bastille. 2 days later, he was dead. That's one of the reasons, incidentally, that I haven't abandoned mathematics for politics. Seems dangerous. But anyway, what Condorcet started doing was he started investigating voting systems. And when all you've got is a dictator or one of the Louis, who were the kings of France at the time, you don't have much voting to do because that's the guy. That's all there is. In a less complicated, in an election, but one that's fairly straightforward, is one in which you only have 2 candidates. What you do is you vote for your choice. Whoever gets the most votes wins. But what if you have 3 or more candidates, as we often do in American elections? This causes problems. Just go back to 2000 and you can see what happened when Nader managed to foul up the 2000 election to such an extent that the election finally had to be decided by the Supreme Court. Now, if you take a look at the problems that one encounters when you have 3 people in an election, there are all sorts of different systems that you can use. For instance, many electoral areas use runoff between the top 2 candidates. What they do is they have an initial election, they take the top 2 candidates, those 2 have a runoff. The problem here is that this is expensive. You have several different elections. And when you have multiple elections, there's, as I say, more expense, more time consuming. So one way of getting around this is a method which is used in several countries. Australia is one, and is also used in a bunch of local elections in the United States, and it's called IRV. What you do in IRV is you rank all the candidates. Every person has a ballot. You rank the candidates, however many there are, your first choice, your second choice, and your third choice. And what you do is something akin to what they do on the television show Survivor. What happens with Survivor is that the person who gets the least first place votes gets voted off the island. You see who's left, who got the least first place votes now. You get them off the island, and finally you're down to 2 candidates, and it's a normal election. So the advantage of IRV, which I think stands for independent runoff voting, means that you no longer have to conduct 2 different elections. You can do it all at once. And several places have decided that this is a good way to go. But the Marquis de Condorcet in studying voting systems, learned that there were problems when one had more than 2 candidates. And one of the problems can be illustrated by a chart that I'm about to put up. But the Marquis de Condorcet was investigating a property that mathematicians call transitivity. It's very easy to understand what transitivity is by looking at numerical comparison. Bill Gates has more money than Arnold Schwarzenegger. Arnold Schwarzenegger has more money than me. Therefore, Bill Gates has more money than I do. Transitivity works great for numerical comparisons. On the other hand, it doesn't work so good for friends. For instance, my wife is a friend of mine, or at least she was when I left this morning. And my wife has a bunch of friends, some of which are friends of mine, some aren't. So friendship isn't transitive. Everybody has friends whose friends are not friends of yours. So friendship is not a transitive idea. But what the Marquis de Condorcet noticed is that even though individual preference in an election is transitive, go back to just a very short period of time. If you preferred Obama to Clinton and you preferred Clinton to McCain, when the time came to pull a lever between Obama and McCain, you weren't pulling the red one. You were pulling the Obama lever, because if you prefer Obama to Clinton and Clinton to McCain, you obviously prefer Obama to McCain. That's transitivity for individual preference. But what Condorcet noticed is that transitivity is not, or rather majority preference is not transitive. And to do that, I'd like you to look at this chart. What this chart is, we have an electoral group of 100 people. 40 plus 35 is 75, 25 is 100. And each of the 100 people marked a ballot between 3 candidates, A, B, and C. And they indicated their first choice, second choice, and third choice. And if you take a look, take a look at how many people prefer A to B. 40 in the first row, 25 in the second. So 65 people, a majority, prefer A to B. And if you take a look at how many people prefer B to C, well, in the first row, 40 prefer B to C. In the second row, 35 prefer B to C. That's a total of 75. A majority prefer B to C. So if majority preference were transitive, a majority would prefer A to C. And if you take a look, unfortunately, that's not the case, because if you look at rows 2 and 3, 35 people prefer C to A in row 2, 25 people prefer C to A in row 3, so a majority prefer C to A. The fact that majority preference is not transitive, and so it's not like individual preference, is known as Condorcet's paradox. And it turns out that I love great examples, because great examples fulfill several different roles at once. And one of the things that happened in the 1940s was they started investigating whether or not there was an ideal way to implement a democratic system. And of course, this happened right after World War II, when all the dictatorships had collapsed, democracy was on the rise, and people were looking for ways to resolve this problem. And everybody knows that if you have an election and the winner dies, you've got a problem. I'm sorry, but what happens if you have an election and the loser dies? You wouldn't think there would be a problem. But watch what happens in this case. Now, this is why this is, a lovely example, because I only have to use one transparency. Let's suppose that you have saving the university money. Remember that, Arnold. Okay, let's suppose that you have an electoral system, that you've got these ballots, and whatever the electoral system is, you've decided that A is the winner. Now B dies. Remove B from the picture. So you have 40 people prefer A to C, but in these two rows, 75 people prefer C to A. So your original winner was A, B dies, you count the ballots again, C is the winner. Okay, let's suppose that B won the election and C dies. Eliminate C. Let's see now, I think I can probably do this by doing it this way. Okay, B was the original winner, C dies, and if you take a look in row 1 and row 3, 65 people prefer to A to B, new winner. And finally, you can sort of see what's coming. Suppose C wins the election by whatever method you're using, and A dies. Well, if A dies, if you look at the first two rows, 75 people prefer B to C. Again, you have a new winner. Now, this may strike you as perhaps, okay, it's sort of a weird thing about elections, but I think I can bring it home in a little more graphic a fashion. Let's suppose that 100 people are going out to dinner, and they have a choice of three different items on the menu. They can either have chicken, or they can have fish, or they can have pasta. And so what happens is they call up the restaurant and they say, the restaurant says, that's too complicated. All we can do is, if we're going to prepare 100 orders, all we can do is prepare one dish. Tell you what we'll do. We'll give you a good price, but you got to come up with one dish. So what the organization does is it submits ballots to all the people with A, B, and C representing chicken, fish, and pasta. And whatever happens, somebody counts the ballots and they say, okay, chicken's the winner. So they call up the restaurant and the guy says, we'd like chicken. And the chef says, I'm sorry to tell you this, but we're out of fish. Okay, we'll switch to pasta. Weird. Think about it. That's essentially one of the problems that happens with voting systems. And what happened in the late 1940s was Kenneth Arrow, who was a graduate student at Stanford at the time, started investigating situations like this. And what he discovered was what I quoted as Arrow's impossibility theorem. And he discovered that there were a bunch of situations that if you asked them to occur simultaneously, you couldn't find a voting system that satisfied this. You cannot find a voting system which satisfies transitivity of group preference. In other words, if the group prefers A to B and the group prefers B to C, then the group must prefer A to C. You can't have it satisfy the dead loser condition. You can't have a dictator in it, because if you have a dictator, one person just chooses what happens and that there are no remaining problems. And finally, if everybody in the group prefers A to B, then the group preference should prefer A to B. These all seem like reasonable conditions, but they simply couldn't happen simultaneously. And when this was published in the early 1950s, ton of research done in this area. Arrow won the Nobel Prize in 1972 for this work. And what happens with mathematicians is when somebody comes up with a novel result, other mathematicians think to themselves, reminds me of a problem on which I've been working. And that's what happened to various other people who were looking at the problem of representation. Now, representation in a democracy is a major problem. The problem of constructing the House of Representatives, how many representatives each state should get, was such an important problem that Washington submitted a suggested way of doing it. Jefferson suggested submitted a way to do this. But the one that was originally decided on was devised by Alexander Hamilton. I think he was the first Secretary of the Treasury, and I'm pretty sure he did this before the duel with Aaron Burr. But in any way, to get an idea of how this particular method, known as the Hamilton method, works, what I've done is, if you take a look at the California counties, we all know California is a weird state, but there's no other state which has three two-syllable, four-letter word counties, all of which end in O. Inyo County, Mono County, and Yolo County. So let's suppose that these people get together to form Inmoyo, first two letters of each. And Inmoyo is an organization which is going to have 13 representatives from the counties. And if you look at the population, I made up these numbers. So I don't know what the appropriate numbers are, but I made them up to illustrate the idea. I assumed that Inyo had 45% of the population, Mono had 40% of the population, Yolo had 15% of the population. And what you can do for each county is determine a quota. And the quota is very easy. What you do is you multiply, to determine the quota that Inyo County gets, you simply take 45% of 13. So Inyo County is entitled to 5.85 representatives. And Mono County is entitled to 5.20 representatives. That's 40% of 13. That's the easy one. And that you don't need the calculator for. And Yolo is entitled to 1.95 representatives. So how are you going to give each of the counties a whole number of representatives? Here's the Hamilton method. What you do is, and I've written that in the second group of numbers. What you do is you start with the quota and you make an initial assignment consisting of the integer part of each one of the numbers. So of that, Inyo is initially entitled to 5, Mono is initially entitled to 5, and Yolo is initially entitled to 1. Now you look at the leftover fraction, which for Inyo is 0.85, for Mono is 0.20, and for Yolo is 0.95. Initially, you've assigned 11 of the 13 representatives. So that means you've got 2 still that you have to assign. And so what you do is you look at the fractional part, and because you have 2 to assign, you take the 2 largest fractional parts. In this case, Yolo and Inyo had the 2 largest of the 3 fractional parts. There are still 2 representatives to assign. So I put an asterisk here, and so Inyo ends up with 6, Yolo ends up with 2, and Mono ends up with 5. And this is the Hamilton method. And it was used pretty much successfully with no real problems until 1880. Now, I don't know why all the people who go into science or mathematics go into it, but I went into it partially because, I had a knack for it, but also partially because there's a thrill of discovery when you stumble on something new that nobody has ever seen before or nobody has ever explained before that is an experience like no other. Galileo experienced it when he saw the moons of Jupiter. Darwin, whose 200th birthday just occurred a few days ago, he experienced it when he devised the origin of species. But it's subtler if you're a mathematician. Because, we don't deal with these real physical ideas that the other sciences deal with. And so the thrill of discovery is somewhat subtler. And it occurred to an individual named Charles Seton in 1880. Charles Seton was the chief clerk of the U.S. Census back in 1880. And back then, the word computer meant, hey, that's what I do for a living. I multiply, add, subtract, and divide, and compute things. And before they invented these wonderful little boxes, a computer was actually a job profession. And most of the people in the Census Department were computers. And 1880 was a census. And Seton did not know how many representatives were going to be awarded to each of the various different states. So what he decided to do was he took the results of the census of 1880 and constructed, via the Hamilton method, the representative assignment for any number of representatives in the House of Representatives from 275 up to 350. Now, if I were to give you an Excel spreadsheet and 20 minutes, you could write the program and do it. But think of the difficulty of doing this back in 1880 when you had no calculational devices like this. You had populations like 8,341,919. You had to figure out what fraction that was of the entire population, doing only long division. Just an absolutely back-breaking task. But what happened was Seton discovered something genuinely interesting when he started doing this. What he discovered was something called the Alabama paradox. Now, if he were a mathematician, it would be called Seton's paradox, so he sort of went into the wrong business. But here's the Alabama paradox, which arose in 1880. If you looked at a House of Representatives which had 299 seats, the state of Alabama got 8 seats. If you increase the number of representatives in the House of Representatives from 299 to 300 and use the Hamilton method, Alabama's representation goes down from 8 seats to 7 seats. Now, remember what I said, discovery in mathematics is a little more subtle, but you look at numbers like this and your eyes pop, because you would expect that if there are more representatives in the House of Representatives, well, each state should either have the same number of representatives as before, maybe one of them goes up one, but you would not expect one of the states to go down in representation. So this was certainly a glitch in the Hamilton method of determining representatives. And so they decided they'd live with this for a while, and they lived with this until 1900 when they encountered, in another census, they encountered the population paradox. Now, the population paradox is not so weird a thing, because at that time, Virginia was growing more rapidly than Maine, but Maine gained a seat in the House while Virginia lost a seat. Now, you would think that if one state is growing more rapidly than another state, it would gain representatives at the expense maybe of the other state. But if you think about it, okay, if you take a really large state that's growing more slowly than a really small state, you could still see how this might happen. So I'm not exactly sure that this qualifies as a paradox the way the Alabama paradox does, but it's called the population paradox. And so the representatives hung on to the Hamilton method until 1907 when we hit the new states paradox. The way they handled changing the House of Representatives when a new state was added to the Union, in 1907, Oklahoma was added to the Union. And what they did was that they'd look at the current number of seats in the House of Representatives, and they'd look at the percentage of the current population that the new state had. And if the new state had 10% of the current population, they would just add 10% more representatives to the House of Representatives, say, taking it up from 300 to 330, and then do the Hamilton method all over again. Well, when they used the Hamilton method again, Oklahoma entered the Union, adding seats to the House to accommodate Oklahoma, but Maine gained a seat in the House while New York lost a seat. Maine seems to be the villain in both the population paradox and the new states paradox, but I think it was just coincidence. Anyway, so what happened? This was more than they could tolerate. And so after scratching their heads, they went to a more sophisticated system of assigning representatives. It's the one that's currently in use today, the Huntington-Hill method, but the Huntington-Hill method is not perfect. And remember what I said about mathematicians saying that reminds me of a problem that I was working on? Well, two mathematicians, Belinsky and Young, were looking at Arrow's theorem, and they said maybe some of the ideas here can be adopted to representation. And what they discovered was that if you have a quota method, now what distinguishes a quota method is that if you look at someone's quota assignment of 5.85, you have to give them either 5 representatives or 6 representatives. You don't have a choice of giving them 3 or 19 or whatever, because these are the two integers that are closest. That's what a quota method is. They looked at, they managed to prove in much the same spirit, although not the same way, that Arrow had proved that a certain electoral system was impossible, was that it was not possible to construct a quota method which simultaneously avoided the Alabama paradox and the population paradox. So what's happened in the 20th century is you have mathematics showing that the universe in many different areas has limitations. Now, I know we started a little late. I don't know whether I have time for one more example or whether you want me to wrap it up. Okay. I wanted to do a brief discussion of Gödel's theorem simply because it's one of the great results in mathematics. And in order to give you a flavor of this, when we think of propositions in mathematics, some of them are pretty straightforward, but mathematics is about patterns. And here's a pattern that I've always found very attractive. Most mathematicians will too. If you add up the odd numbers, they're squares. 1 is 1 times 1. 1 plus 3 is 2 times 2. 1 plus 3 plus 5 is 3 times 3. 1 plus 3 plus 5 plus 7 is 4 times 4. Now, if you're a mathematician, you wonder whether or not this pattern goes throughout all the integers. And there are 2 different ways that you might decide to go about this. One way is to check all the integers one at a time until you either find a counterexample, an integer for which it doesn't work, or you manage to show that they're all true. There's a problem with that. If you don't find a counterexample, it's going to take you forever to get through checking all the single cases because there are an infinite number of integers. That's probably the reason that the idea of mathematical proof arose, because there are things that you want to say that they're always true, so you look for mathematical proof. Now, there are lots of ways that mathematicians prove things, but what I'd like to do is, instead of showing you a proof by induction, which can be done for this, or a proof by algebra, I just like to show you some pictures. So what I'm going to do is I'm going to draw the black dots in, let me show you the 2 different things. The white dots are what you previously had, or the white dot in this instance. The black dots are the last number to be added. So you can see here that when you start with the 1 white dot from the previous case and add 3 black dots, you get a 2 by 2 square. So now what I'm going to do is I'm going to color all these dots white and add 5 more around the edges. You get a 3 by 3 square. Color all these 3 by 3 dots white, add 7 dots around the edges, you get a square. Maybe not a formal mathematical proof that you could write up in a journal, but you show it to any mathematician and they say, yeah, it's cool, we've proved it. And the amazing thing that Godel did was he showed that there are propositions. And to this date, the problem with what Godel did is he showed that a proposition which really didn't have any mathematical significance whatsoever. It wasn't something like that's a beautiful pattern like this. It's a very awkward and artificial type of proposition. But he showed that there was a proposition involving the integers that you could neither find a proof for it logically or prove that there, or discover a counterexample. So this was all of a sudden, this was in a hazy never land that mathematics had never suspected existed before, that there are propositions which are true, but that mathematics cannot prove. And this not only changed mathematics, but it also changed philosophy. There are entire branches of philosophy which are built up on the logical systems that Godel worked with, extending the logical systems, seeing what the limitations of these logical systems are. And if you look at what has happened in the 20th century, there are some people, we're living in a time of budget problems, and people are gloomy because of them. But Laura struck a very optimistic note. And some of the same thing happens when you find that that might happen when you see a dead end in mathematics or science. You say, okay, we've hit the wall. But if you look at some of the things that happen when you hit the wall, Isaac Newton spent 10 years of his life on alchemy, went nowhere. In fact, it went so nowhere that he buried his notes for 300 years and said, nobody's to look at this for 300 years. And when they unearthed it, there were no great truths there. I could see a great Robert Ludlum novel once they, didn't happen. There was really nothing of interest because he was pursuing alchemy without the basic understanding of the atomic theory, which rendered any concept such as the discovery of the philosopher's stone, which would transmute base metals into gold. You can't do that. And if Newton had known that, he probably wouldn't have worked on alchemy. He would have done more physics and mathematics, or he might have been working in chemistry. And if you look at what happened to alchemy, alchemy's a dead end except for writing Harry Potter novels or whatever. But if you look at it, alchemy morphed into chemistry. And the world that we have today is the outgrowth. If I were to ask most people what's the most important of the sciences in their lives, how it most impacts their lives, my feeling is it's probably chemistry. It's a toss-up between that and maybe physics. The only reason that biology is a little behind it is because biology was the last of the sciences to really come under systematic scrutiny. It took a while to overcome some of the prejudices that were involved in looking at biological structures, and it took a longer time to work with the complex structures that biology deals with. Biology deals with much more complex structures than either chemistry or mathematics or physics. And the more complex the structure, the more difficult the problem. We get back to the garage. They have the more complicated things too. So I'd like to close just by saying that I feel that it's important to look for the dead ends as well as what you can do, because the dead ends show you what you can't do, and then maybe you know how to allocate your resources a little better. And hey, those of you legislators that are locked up in the Capitol in Sacramento, you might pay a little attention to that. Thank you very much. As Beethoven would have heard them as he progressed through his career. And you could hear that, the first few symphonies he heard perfectly fine, but you could hear the quality of the hearing get worse. And by the end, I don't think he was totally deaf for the Ninth Symphony. He could hear sounds. He could hear volumes in certain tones, but he certainly couldn't hear the depth of the music that he had created. But nonetheless, it's like the blind geometers, that he wasn't deaf from birth. To me, it's just as impossible to imagine how one could compose music if one were deaf from birth as it is to do geometry if one is blind from birth. But there is a difference, because music is a purely sensual experience, or purely sensory experience, whereas geometry is an intellectual one. It's possible to set up an axiom system for any one of the geometries and describe it abstractly without ever seeing the structures that you are discussing. You can say what a triangle is, what a line segment is. You can give the properties and the theorems without ever drawing the triangles and line segments. Am I right, Robert?
Yeah, you can.
Yeah, I mean, you wouldn't, of course. You wouldn't, of course, in a geometry course because you get the ideas from the pictures. But that, that illustrates one of the ideas that a lot of the mathematicians have looked at, the ideas of models of mathematical structures. And that was, okay, I hate to plug the book because I just feel, I sort of feel like a shill. But one of the things that I was investigating and looked at for the book was the idea of different models for various axiomatic structures. And there was a tremendously interesting question in the 19th century that was tackled by several mathematicians. Is the Euclidean plane as we know it the only model for the axioms of Euclidean? I can draw something. Love it. Okay. If you learned Euclidean geometry the way I did, here's a line L, here's a point P, and one of the axioms in Euclidean geometry is through every line, through every point off a given line, there's one and only one line parallel to the original one. And mathematicians had wondered for generations whether or not this axiom was really necessary. It's called the parallel axiom. Could it be proven from the other axioms? And if it were necessary, is the plane the only model in which this is true? And in the 19th century, a couple of different mathematicians managed to show that this is not the plane is not the only model. In fact, what you can do is you can draw models in which there are no parallel lines through a point to a given line, and where there are infinitely many lines through a point. They're different surfaces. They're not on a flat plane. They're sort of on bizarrely shaped surfaces. But nonetheless, this is the way that mathematics develops. Mathematics looks at questions in the abstract, poses questions, and one of the true joys at least for me, probably the high point of my mathematical career was I wrote a paper back in 1972 or 1973. It was very abstract. Got written up in a journal. 5 people ordered reprints of it or asked me for reprints. So I had 45 left because the journals always send you 50, sitting on a shelf. 8 years go by. All of a sudden, I get a flood of requests for this article from electrical engineers from all over the world, and I ran out of copies, and so I wondered what the hell was happening. And somebody had taken the stuff that I did, which was purely abstract mathematics, and adapted it to showing that it had practical use in something called signal processors. Signal processors are devices from electrical engineering, which, not surprisingly, are used to process signals. And what I'm sure many of you have had the following experience. You've turned on something like your amplifier or on a piece of auditory equipment, and you hear the squeal, that just destroys your ears. My theorem tells you when and when not that squeal occurs. Okay, not up there with Newton. But nonetheless, I look at it this way. Something that I did that was truly abstract, and I've spent all my life in abstract mathematics. It's something, and it's one of the pleasures of mathematics that actually gets used for practical purposes. And this has happened time and again. This is the story of mathematics. The Italian differential geometers of the late 19th century, working out the mathematics of these obscure surfaces, nobody cares. And then all of a sudden, Einstein comes along and he shows that this is the mathematics that describes the universe and the theory of relativity. And this is one of the pleasures of mathematics is that it has so many different applications and occurs in so many different areas. Who would have believed that it would show you that there are problems that you can't implement a perfect democracy, or you can't come up with a really perfect way of structuring the House of Representatives? It's fascinating.